Hey everybody, this is Mr. Canfield for our lesson on u-substitution. U-substitution is essentially how we get around the chain rule, product quotient rule, all those different things, kind of trying to go in reverse with them. So we've learned lots of antiderivatives, but there's still so many that we can't do, or some that would just be really, really unfun, like 4x plus 1 to the 30th. Well, yeah, I could FOIL that out and eventually figure it out, but there's got to be an easier way to do that, or at least we would hope, and there is. Or then something like this, 3x plus 8, the square root of it. Well, we really don't have a way to go backwards from that, besides like kind of fudging our way there, guessing and checking and figuring something out. Same thing with this, sine of 2x, and then something like this. This is, even with the tool that we're learning today, we're going to find that this is actually particularly difficult. So buckle up, let's get into it. So oh, right, yeah, no, I like to skip this part. All right. So the way that I handle u-substitution is as follows. So let's say we have the integral of x squared plus 1, all that cubed, times 2x dx. What we're going to do is we're going to look and try to find the deepest, farthest inside piece of parentheses. So we'll say step 1 is look within. This isn't like a self-reflection thing, I'm just being a little bit silly. So the first thing we're gonna do is we're gonna look within. So I see I have this big thing cubed, I have a 2x, I have an x squared plus 1. This x squared plus 1 is really inside of this parentheses. So I like to say, what's the farthest thing inside parentheses? Then we're gonna call this u. And if we were to do that, we could think about this as being the integral of u cubed 2x dx. Which right now, like, the big thing that I want you to understand is that if I were to call x squared plus 1, if I were to call that u, the big thing that I want you to understand is that instead of writing x squared plus 1, I could write a u there, and so it would say u cubed. And our goal with u-substitution is to eventually be completely out of the x world and be completely in the u world. So we're going to look within, we're going to find you, or find yourself. If we're, using this stupid analogy, look within, find yourself. And I'm gonna stop, but we're eventually gonna take the derivative of you. We're gonna find the change of you. We're gonna change yourself. I'm not gonna write that because it's really bad. So we're gonna do u prime next. So if I were to call this u, and I take the derivative, du dx is equal to 2x. And then we want to solve for du by multiplying both sides by dx. So dx, dx, dx is cancel over here. We almost always skip writing this step. We almost always will just go u is equal to x squared plus 1, du is equal to 2x dx. This step right here is there just in case you find that you're forgetting things. You might want to always write this. It's really down to personal preference. Nobody is going to be upset with you if you skip this step and go from here to here. This is the way I'm usually going to write it on the board. So let's see what I wrote here. Since 2x dx is equal to du, we can replace 2x dx with du. So we looked within, we found u, we did u prime, and then leave the x world. So we need to be completely out of the x world. So see how here I have u's and x's together? That's not good. So what we're going to be able to do is see how this says 2x dx here. Well, that's exactly what this says. So instead of writing 2x dx, I'm going to be able to replace it with what it equals, which is just du. So I'm going to be able to actually write this as the integral of u cubed du. Now remember, when we do integrals, the variable's a dummy. It doesn't matter what that variable is. So I can take this integral like I normally would, which is what happens down here. So now that we're completely in the u world, we're going to integrate as normal. I don't know if that's maybe I should say integrate as usual. Oh well, I've already written it. So we get u cubed, we add the 1 divided by 4 plus c. And then the last thing we do is back to x world. So the reason I'm talking about the u world and the x world is a little bit later when we look at the bounds, it's helpful for us to remember that, oh, these bounds are in the x world. We want to make them u world bounds. And I found that was particularly helpful with my BC students when we were reviewing this concept. So that's why I'm already starting with that language. So you'll notice we took the u cubed du, u to the 4th over 4 plus c. And then we just go, well, wait, what was u? U was x squared plus 1, and we just drop it back in. And this is a technique to get around integrals that we're not sure what they do. It takes care of all the little bits and pieces. And let's just double check. Let's take the derivative of this. So this is saying 1/4 x squared plus 1 to the 4th power plus c. So if we took the derivative of this, well, we'd bring the 4 out front. 4 times our 1/4 x squared plus 1 to the 3rd times 2x, and the c would just turn into a 0. And 4 times the 4th cancels, we just get 1. We get x squared plus 1 cubed times 2x. Oh, hey, that's the original problem. Oh dear. I think I've drawn worse happy faces in my life. But yeah, that's all it is. So for those of you that want the short version, this is going to handle a majority of what we do. Now, finding you and finding yourself, that's the hard part. Picking the right thing for you is really the hard part. And I do really enjoy the silliness of, you know, the introspection that this is pretending we're doing. Oh yeah, I'm thinking about myself. No, just, okay. So let's see. So the first thing I'm gonna do is I'm gonna look within. All right, let's see. I see this looks like it's inside. What if I set that equal to u? Now, on the last page, I don't know if I didn't say it out loud, but I don't know if you saw it. I like to put my u work over here to the left. So generally what I'll do is I'll put my u stuff over here and I'll say equals, and I'll write my u world stuff right here. So let me say u is equal to 3x squared plus 1. Notice how u is not including that squared on the outside. U is the inside stuff. So I think that's what u is. Now I'll take my du. So I'm going to write this step one time, and then I'm not going to do this again. Du dx. So du dx is equal to, let's see, 6x. So then we'll multiply both sides by dx. So I get du is equal to 6x dx. Uh-oh. Okay, this is a fake pause. We should experience some level of cognitive dissonance here. Our brain should go, wait a minute. Last time, so this, we can say this is u squared, but I have 6xd, this and this don't match. And so what we want to do is to leave the x world, we need to make these match. And how could I make these match? Well, if that 6 wasn't there, they would match. And so I use algebra rules. I'll divide both sides by 6 and get 1/6 du is equal to x dx. Now I have a perfect match. So now, instead of writing x dx, I can write this very well written 1/6 du. Now this is a really ugly way to write it. I normally just start going down from here. I'm gonna actually rewrite one more time. This is a constant. This is u squared times a constant times du, so I can bring the 1/6 out front. Remember, when there's a constant inside, multiply by everything, you just pull it out front of an integral. U squared du. Okay. And now I can just integrate as normally, because I have completely left the x world. I'm completely in the u world. So I've got my 1/6, then we'll add the power, divide by the new power, plus c. So I've got u cubed over 18 plus c. And now all I've got to do is go back to the x world using u is equal to 3x squared plus 1. And so what this is doing is this is helping us take care of the fact that when I take the derivative of the inside stuff, I wind up getting a 6x, and there's that 3 that happened. It's taking care of all those things. All right, let's look at our next one. The integral of 4x plus 1 to the 30th. I think this was one of the ones on our first page. Yeah, this was the very first one that I pointed at earlier. So let me look at this one. All right, well, look within. Now this one's really easy to figure out what u is because there's just the parentheses and that's all there is. So I'm going to say 4x plus 1 is equal to u. So then du is equal to 4 dx. See, that's the normal way that I'm going to do it. I'm going to skip that middle step. So I'm almost able to completely eliminate stuff here. I'm able to say u to the 30th, but this dx has a 4 on it. It says 4 dx. It doesn't say just dx. So I'm going to have to divide both sides by 4 and get 1/4 du is equal to dx. So I'm going to pull the 1/4 out front, du. So very, very similar to our last one, except I'm kind of doing the steps as I actually would on my own. So in case you missed that, it was something like this, and then I pulled the fraction up front. So now when we integrate, we get u to the 31 over 31. Whoa, what a pleasant number. Then we have our plus c. And I want to say I don't care what 4 times 31 is, but 4 times 30 is 120. And then there's one more 4, so it's 124. If this were a free response question, I wouldn't have to find that. And now I'm just going back to the x world. So I left the u world, back to the x world, call it a day. All right, let's see what's next. So shout outs to Megan and Stevie for your suggestions. I hope that I'm doing things a little bit better. All right, let's see what's next. Okay. This one might be harder for us to see, but also I don't have it in the format that I like, but that's okay. I just did it before, right? Okay, so this next one, I can say 3x plus 8, so that means that we can do, this is 3x plus 8 to the 1/2, right? That might be worth thinking about. So the farthest inside is this 3x plus 8, so we can say u is equal to 3x plus 8. So then our du is equal to 3 dx. It's very similar to the previous one, so I'm going to have to say 1/3 du is equal to dx. And a lot of you are going to get to a point where you can do that really quickly, and that's great. So we can say that this is, let's see, I'll pull the 1/3 out front, u to the 1/2 du. Now that's a really nice integral because it's just u to the 3/2 times 2/3. The 1/3 is out front, du. We're going to get in 2/9 u to the 3/2 plus c. Oh, I got ahead of myself, sorry. Gotta slow down. So That's one reason I don't like to go too fast in these videos, is that I have a tendency to make silly mistakes when I go too fast. So, all right, so now that I've taken my integral, normally I'll just plug back in my 3x plus 8 and call it a day. All right. On to our next one. All right, let me see. I'm gonna look within. Now this one might be a little bit harder to find out what's within, but that might sound really patronizing. it's the 5x. So if I were to say u is equal to 5x, then that would mean that du is equal to 5dx. So I don't know if you can see it, but this time the 5 and the dx are actually there. Like I could have rewritten this as like cosine of 5x times 5 dx. And so it's just a complete substitution right there. So I actually can rewrite this as cosine of u du. No manipulation over here necessary because there's a perfect matchup. So if I take the antiderivative of this, I get sine of u plus c. Right, and I like to double check these because I mix up my signs on these because, you know, the derivative of cosine is negative sine. Wait, is this one negative? So the derivative of sine goes back to cosine. Okay, yeah, no need to throw a negative on there. And then I'll just have to throw in the 5x. And now that question on our last quiz that most of you weren't sure how to handle, boom, there we go. And I know that I put it on there, and I know that I hadn't taught you this yet. I wanted to see if you could figure it out. It was 1 point on the whole thing. It was like 3%. That's what I can use to say, oh, this person got an A, oh, this person got a high A. If you didn't get it, you still, okay. You're not arguing with me right now. Well, I mean, if you are, I can't hear you. Okay. So now we start getting into strangeness at the look within step and finding yourself. We want to see, do I see a derivative? So what I mean by that is when I look here, do I see something where when I take its derivative, that derivative is actually here? And so this example, I do give you a hint. I give you a hint that sine squared is equal to sine of x squared. And so if instead of writing it like this, if we were to think about it like this, sine of 3x, cosine of 3x dx. Okay, if we were to think about it as sine of 3x, all of that squared, times cosine of 3x dx. Kind of going off of the way that I talked about this earlier, you would want to say, oh, the 3x is going to be my u. But if we do that, I'm going to do this on here. If we were to make 3x equal to u, sorry, I got interrupted. Okay, so if we said u is equal to 3x, then du is equal to 3dx. And if I were to try substituting here, I guess I'd have to say 1/3 du is equal to dx. When I go back in, I guess I wouldn't have done all that. I would have just said that there. But we would get the integral of sine squared u cosine u du with a 1/3 out front. I don't know this antiderivative. This tells me that the u that I picked isn't helpful. There are going to be times when there's more than one u to pick, actually. But in this situation, picking this for u kind of failed us. And so instead, we want to try to find something that we take the derivative of and we get something else that we see. And so if I were to set u equal to sine of 3x, when we take du this time and we get cosine of 3x with a 3 out front, now we have, oh, Max is interrupting us. Okay, sorry about that, got interrupted. So if we said du is equal to 3 cosine 3x dx, well, Well, check it out. What can we eliminate so far? Well, I see cosine 3x dx on the end. We'll just have to divide by the 3 and get 1/3 du is equal to cosine 3x dx. And now I'm going to be able to substitute everything. I'm going to be able to say this is 1/3 times the integral u squared, and cosine 3x dx goes away. And we can really think about this like this now. It's just a 1/3 times u squared. So we get u to the 3rd over 3 times our 1/3 plus c. And so it's going to give us cosine 3x, all that cubed over 9 plus c. And we're good to go. Nope, that's totally wrong. When you sub back in, you want to make sure you put u in, not du, Canfield. All right, so sine 3x over 9 plus c, all that cubed. So we could say sine cubed of 3x as well, and that'd be the way it would show up on a multiple choice. And this level of problem, this would never be anything more than a multiple choice, because they don't usually just have you take an integral. They're usually going to have you do something with it. So for this next one, we have to decide which one is inside, which one is u. Look within. Well, what's the derivative of this one? 2. I don't see that anywhere. What's the derivative of this one? 2x plus 1. Oh, well, would you look at that? The derivative of this is right there. So if I were to say that u is, wait, pause, Canfield, pause, hold on. I knew to do that because this is u-substitution, because that's all we're thinking about in this lesson. But if I didn't know that, maybe I would actually prefer to FOIL this out and get x squared times 2x is 2x cubed, then plus 2x squared, then plus x squared, then plus x, and get 2x cubed plus 3x squared plus x dx. And maybe I'd prefer just to take the integral just like this and get x to the 4th over 4 with the 2 still there, plus 3x cubed over 3 plus x squared over 2 plus c. This would be correct. It'd be absolutely correct. There'd be nothing wrong with doing that. But since we're in u-substitution, I want to show you that tactic, that technique. So this is one way for us to find the indefinite integral of this. So since we're in u-substitution though, let's say u is equal to x squared plus x, then du is equal to 2x plus 1 dx. Well, would you look at that? We have a perfect substitution. So when we go and we drop it back in, we get the integral of u du, which is like really nice because the antiderivative of this is just u squared over 2 plus c. And when we drop stuff back in to get to the x world, we get our x squared plus x, all that squared over 2 plus c, and we're done. This is actually less work than doing the other way. But it's a different kind of work, and so you might not prefer this way, you might prefer the other way. However, we kind of need to be ready. If I do it this way and I don't see my answer, then I'm going to have to do some work. I'm going to have to say, well, this is x to the 4th over 2 plus x cubed plus x squared plus c. Well, what could I do to this? Still over 2. There's some work we're going to have to do to figure out how to get this back into that. Or I guess you'd have to FOIL out the different answers and see which one matches yours. But yeah, it's not always super straightforward. So now with our next one, so I'm going to look within. All right. So on this next one, it might not be readily apparent, but we've got two different things. Let's look at their derivatives. So the first one would be 2 tan x, oh, that's promising, times secant squared. Never mind, that's not promising. This one, let's see. Secant squared. Also not promising. I don't see either of their derivatives. And hopefully what you're thinking is, well, maybe there's a trigonometric identity that I could apply here. Remember that sine squared plus cosine squared is equal to 1. And I see tangent, so let me make tangent. I know tangent's sine divided by cosine, so let's divide both sides by cosine. We get tangent squared plus 1 is equal to secant squared. So I actually could do a replacement here and say that this is secant squared times tangent. And now the derivative of tangent is present, so I can say u is equal to tangent of x. So du is equal to secant squared x dx. And this is actually a perfect u substitution now. So I can say that it is u du. If that was too fast, the tangent was u, and then secant squared dx, the leftovers, was du. And so we get u squared over 2 plus c. So our final answer, we could say tangent squared over 2 plus c. This is a tricky question. All right, on to our next tricky question. All right, so there is a tactic called double U substitution. Not W substitution, but double U substitution. And basically what we need to do is every now and then we're going to need to take our formula for U and mess with it a little bit to do some substitutions to make this something that's integrable. So I'm going to do my fake work first, then I'll do my real work second. So fake work first. Okay, I see far inside here, I see u is equal to x minus 1. So if I do that, I say u is equal to x minus 1. Then du is equal to 1 dx. So if I were to do my replacement, why am I talking like this? Sorry. We do a replacement, we get the square root of u du with an x out front. I need to completely leave the x world. So that is not okay. This doesn't work. It failed. So perhaps I need to pick x is equal to u. Let me try that. Well, then dx is equal to du. Oh, I wrote it in the wrong order. If I tried that, I'd get u times u minus 1d. This and this are identical. I just wrote a different letter. This isn't helpful either. Scared yet? It's not as bad as it might seem. So shaky cam. The tactic that we use, we say u is equal to x minus 1. That was the correct u. And du is in fact equal to dx. And that does allow for a good deal of substitution. I just wish that that wasn't there. And instead of writing square root of u, let's write that as u to the 1/2. Why do they put that in parentheses? Whatever. So let's say that's u to the 1/2. That's an integral we know. And what we're going to do is we're going to actually take this, and I'm going to take my u is equal to x minus 1. I'm going to solve this for x. So I'm going to add the 1 to both sides and get u plus 1 is equal to x. And so now when I see x in here, I'm going to be able to replace x with u plus 1. Which it might just seem like we've kind of taken this and rearranged it. And in some ways, that's all we have done. But if we were to distribute the u to the 1/2 here, remember that when we multiply bases, or multiply exponents with the same base, we add them. So 1 plus 1.5 is, or 1 plus 1/2 is 3/2. So I get u to the 3/2 plus u to the 1/2 du. Well, hey, that's an integral we can take now. So using this idea of double u substitution, where we got rid of u normally, or got rid of x normally, and then had to do some playing with our u formula, now we have an integral we can take. So I get u to the 5/2 times 2/5 plus u to the 3/2 times 2/3 plus c. And all I got to do now is sub back in. So 2/5 x minus 1 to the 5/2. And I do not purport, is that the right word? I do not posit, I don't think for a second that this looks nice. I'm not like, oh, that's such an elegant, pretty looking thing. No, it's horrible looking, but it went from, gee, this is impossible, to, hey, now we have a solution. So now look at this one. This one looks even worse. Even worse. So I'm going to kind of do some similar tactics. I'm going to try some things out. If I get it on my first try, I'm going to try it another way. So if I were to say u is equal to x plus 1, because what I think is going to happen is I think we're going to take the x squared plus 3x and we're going to multiply it by u to the negative 1/2. I think that's what we're going to wind up doing. I think we're going to mess with it somehow like that. If I say u is equal to x plus 1, and I said du is equal to dx, and I said that x is equal to u minus 1, well, then what I'm going to be able to do, yeah, I think I got it. What I'm going to be able to do is go back in here and replace all my x's, every single x. And so if we do that, we get u minus 1 squared plus 3 times u minus 1 all over the square root of u. And I want to FOIL the top out, oh sorry, du. I want to FOIL the top out, so let's see, that's u squared minus 2u plus 1 plus 3u minus 3. Combine my like terms, I get my u squared, the negative 2 and the 3 get a positive u. And that gets minus 2. Okay, so my numerator is u squared plus u minus 2. So now I can say that this is the integral of u squared plus u minus 2, all times u to the negative 1/2 du. Really helpful. Because now I can distribute the u to the negative 1/2. Remember, we're adding these exponents, so 2 plus negative 1/2 is 3/2. 1 plus negative 1/2 is 1/2, and then minus 2u to the negative 1/2 du. And now I can integrate this. So we'll add 1 here. We'll get 5/2. Then we'll add 1 here. And then we'll add 1 here. Positive 1/2, so that's going to get times 2. Plus c. And so to finish that up, we'll have our 2 go back to the x world. Oof, oof, oof. Oh cool, I had enough room. The only thing I did was I did the 2 times 2 turn into 4. So I said what u was x plus 1. So a little x plus 1, x plus 1, x plus 1. And we've got our integral. So just let me be clear. If I take this derivative, I'll get back to that. There is no way that I was going to be able to look at that and know that that was this antiderivative. U-substitution makes something like this possible that would have been completely impossible before. All right, we got 2 more pages of this. All right. Okay. All right, okay. Okay, all right. So, when we're looking at using the fundamental theorem of calculus and u-substitution, when we're taking integrals that are now definite, so this says take the integral from 0 to 1 of this, hopefully we can readily see that u is going to be equal to x squared plus 1, so then du is going to be equal to 2x dx. And we're pretty close. We got an x dx, so I'll need to divide both sides by 2 and get 1/2 du is equal to x dx. So I can do my substitution, and if I do that, now I have option 1 and option 2 written here. I'm going to show you option 2. I don't like option 2. I think it's dangerous because if you don't ever learn option 1, there are going to be questions on the AP exam that you're not going to be able to do. And I'll explain a little bit more about that later. But so when I go and I do my substitution, I get my u cubed, and then the x dx is equal to 1/2 du. Now look at my bounds. My bounds are when x is equal to 1 and x is equal to 0. But I am supposed to, if you remember, I'm supposed to leave the x world completely. So if x is equal to 1, I need to figure out how x is equal to 1 is going to carry over into the u world. And so I actually have to go and I have to solve for these new bounds. So if I'm going to do that, let's see. I know u is equal to x squared plus 1. So if x is equal to 1, 1 squared plus 1 is 2, so u is 2. So I get 2 here. And then if x is equal to 0, I get u is equal to 1. So now that I've completely left the x world and we're finding a definite value, I actually don't ever have to go back to the x world. Because now that I've changed everything in terms of u into things in terms of u, now I never have to go back. So check it out. Antiderivative u to the 4th over 4, there's the half out front still, evaluated from 1 to 2. So that's u to the 4th over 8, right? So that's 2 to the 4th over 8 minus 1 to the 4th over 8. And we get 2 to the 4th is 16. And 1 to the 4th is still 1. So we get 15/8. It's a really elegant way to do the problem. And the thing that happens sometimes on the AP exam is they'll give you a multiple choice question and they'll say, use u-substitution and rewrite this integral. And they'll go through, they'll do all this, and this is the correct answer, but then they'll also have 1/2 u cubed du, and they'll leave the bounds in the x world. And this is going to be, we call it a distractor, out of A, B, C, D, E. E might be none of these, and then they'll have 4 other answers. One of the answers is going to be the correct setup with the wrong bounds, because the bounds are supposed to have changed as well if we're going into the u world. And so this is an incorrect way to write this integral. Now, but if you're just solving it, option number 2 you might prefer, and option number 2 is almost the same thing, except we ignore the bounds as we go through. And so we'd say, okay, it's 1/2 times the integral of u cubed du, and then I get u to the 4th over 8, right? I'm skipping my steps a little bit. And then we go back to the x world, x squared plus 1. Right, u was equal to x squared plus 1. So we go back to the x world over to the 4th over 8. And now we evaluate using our x bounds from 0 to 1. Conceptually, this way I think is a little bit easier, but you're not doing yourself any favors doing it this way. Because now I've got to plug number. Okay, now I got to plug 1 in. All right, so let me plug one end, that's 1 squared plus 1 to the 4th over 8 minus 0 squared plus 1 to the 4th over 8, and that's 2 to the 4th over 8 minus 1 to the 4th over 8, so 16 over 8 minus 1 over 8, 15 over 8. Okay, so like same answer, but the problem is you're not going to know how to do this because you're so stuck on going back to the x world. And I'm not trying to point any fingers. I'm just saying that in the past I've noticed that my students who focus on this way get really confused by these kinds of questions. So I'd really, really encourage you, completely leave the x world even with your bounds, integrate as normal, and then if it has bounds, never go back to x. So, oh no, there are more stupid analogies that we can say here. If you put boundaries on yourself, you're never going to go back to your x and keep making mistakes. No, so stupid. Oh dear, I make myself laugh. All right. The last little bit's not technically u-substitution, and I'm going to leave that out. I might do a separate mini lesson on that at some point. But I hope this was helpful. Just remember, big ideas as we go through this. You want to look within and find u. And as we're trying to find u, you want to remember, do I see u's derivative present? Sometimes that's our big clue about what u is. And then you want to find u prime. You want to, you want to get your du and dx separated out and substitute. You want to completely leave the x world. If there's any remnants of x left over, you're not done. We want to integrate as normal. Remember, if it has bounds, once you've left the x world, you never go back to the x world. But if there aren't bounds, if it's just indefinite, you want to go back to the x world at the end and pretend like the u-substitution never happened. Well, I hope this was helpful. I really appreciate your guys' feedback. Please let me know anytime if there's something that you think I should be doing differently, especially if it's easy like this. This was super easy, and I think it even helped me in my explanations. Peace out. Whoa. What am I, 12? No, I'm sick. That's what's wrong. Have a great day.